Let's move it a bit up. I'm gonna remesh it. Gonna increase the resolution a little bit, let's say 0.1. So now we got these triangles. Then I'm gonna give it some constraints. I want to use the cloth constraints. I'm gonna set the mass to uniform and the thickness calculate uniform. Then I'm gonna put down a solver. I'm gonna add a ground and then I'm gonna toggle the real-time playback and let's see. Okay, we got a simple simulation. So what I want to do is I want to use this simulation, but I want to use this render geometry. Maybe even if I subdivide this, maybe something like this. And I'm just going to put down a null for this and call it render geometry, render geo. And to do that, I can use the point deform node. And what this node needs is the geometry to render, which is this one. So I'm just going to put down an object merge. Pick up this one. So it's here. Then I need a rest geometry for the simulation, and its position should be close to or match the render geometry. So I know on the first frame of the simulation, it's in the same place as the render geo. So I'm just going to use a time shift. I'm going to right click and delete this channel, and then I'm going to use the first frame. And then for the deforming geometry, I'm going to use the simulation, and the topology of this geometry needs to match the topology of the rest geometry. That is how the points and the primitives are connected together, but their position can be different. So the rest geometry needs to match the position of the render geometry, and the deforming geometry needs to match the topology of the rest geometry. So now if you play, we got something like this. So, because the points and the primitives of these two need to match, we will get into trouble if we are emitting geometry into the simulation. Let's change the simulation so we are emitting the pighead. So I'm going to put down a circle. I want it to be in Z-axis. Then I'm just going to scatter a point on it. Just one point. And I don't always want it to be in the same position. So I'm going to add the frame number into global seed. So now if you play, we got different position. Then I'm going to copy the pighead to these points. Like this. So we got this, but I do not want to emit on every frame. So I'm just going to delete some of these. So back in here, I'm going to put down a delete node. I want to delete points. I'm going to untoggle this one, and in random, I'm going to enable it and say delete 95% of the points. And for the global seed, I'm going to use the frame number again. So now if we play, we get a point every once in a while. Like this. Then we move it upwards, which is fine. We remesh them, which is fine as well. Inside of the Vellum solver, I'm going to use a Vellum source node. I'm going to set its emission type to its frame. And then I need to reference the simulation geometry and the constraints. So I'm going to go back upstairs and I'm going to put down two nulls. And this one I'm just going to call geo. This is our pighead. And this one, I already put down this null from the second input, which is going to be my constraints. Back inside the solver, I'm going to point this to the geo node. So I have to go up a few hidden levels. So I'm going to go out of this node, up one level, up another one, up one more level, and then it's called geo. And then for the constraints, I'm gonna do the same. Out of this node, up 3 levels, and then it's called con. Let's connect it and go upstairs and play the simulation again. And you can see we're emitting pickets. Some of them are intersecting, so they get stuck together, but it's fine. Now if we check out our point deform, the system is gonna break. And the reason is because, first of all, the render geo doesn't always exist. Second of all, the rest geometry also doesn't exist. And even if it did, the point and primitives and the topology of the rest and the simulation geometries wouldn't match. My way of getting around this is by using geometry solvers. So if we go up here to before the simulation, I want to collect all these pickets and use as a rest geometry. So I'm going to put down a geometry solver that is just called solver. Dive inside and put down a merge node. And now, if we play this, we'll get the pickets, but they will stick around. We are collecting them. So what this node does is it takes the current frame and then whatever was on the previous frame and merges the two geometry together. So each frame is merged with the previous frame, and that way you collect all of the pickets. This simulation starts at frame 1, and the previous frame to frame 1 is frame 0. I do not want to include any geometry from frame 0, so to get around that, I'm just going to use a switch node. And I'm going to say if the current frame number is equal to the first frame of the simulation, then use input number 1. That is the current frame. I'm going to go upstairs and I want to copy the start frame of the simulation. And then in here, I'm going to say if the current frame is equal to, and then paste relative reference, then use the first input. So just in case we have something on frame 0, we're not going to include it because again, down here, the point count needs to match. Then I'm going to put down another null. And I'm just going to call this my rest geometry. We need to do the same for the render geometry. So I'm just going to copy paste this node and use it up here as well. So now if you reset the simulation, let's play again, we are collecting the render geometry. Down here we have the render geometry. We need to update the rest geometry, so I'm going to cut this one, put down another object merge, and I want the rest geometry, this one, rest geo. And now if we play, it will work a little bit better, but we'll run into some issues. And that is because if you look at these pickets up here, these and these, they're so close to each other. So some of the render geometry might be closest to a point of some of the other pickets. And that's why we get these stretched primitives down here. So the points are basically getting confused about which picket it should reference or something like that. But on the point deform node, we have this option to use a piece attribute. And then it will only match the point if the value of the piece attribute matches. So we go back up here. I'm just going to put down a connectivity node. And it's set to class. You can see it down here. It goes from 0 to 5. And if we look at it in color, let's say random from attribute, and it's called class. So the first picket will get the class attribute value of 0. The second one will get 1 and 2 and 3 and so on. Let's do the same to the rest geometry. So I'm going to put down another connectivity and make sure it's also set to class. And now if you plug this into the color, you can see these match. And let's look at them both together. So I'm copy pasting this color node Let's merge them. And then I'm just going to move this one a little bit to the side. And you can see the class attribute values match on the render geometry and on the rest geometry. So back in the point deform node, we can set the piece attribute to class. And now if you play the simulation again, we don't have the stressed polygons anymore. And just make sure, in case you're using some sub-steps on the Vellum solver, that this Vellum source is set to each frame. Because if it's set to each sub-steps, we will need to match these sub-steps to whatever sub-steps we have on the geometry solver. So the easiest way is just to keep the sub-steps of both these solvers as 1, and then use each frame for the Vellum source. Another thing to look out for is sometimes these solvers might not update. So if you're getting something weird, you might just want to hit reset simulation on these two, just to make sure that you have the latest geometry in case you make some updates up here. So I just realized that we might get in trouble if we have anything on the first frame. Because I think we might get double the geometry on the first frame because the Vellum source will pick it up as well. So let's just try to see if that happens. So I'm just gonna copy paste this guy. And I'm gonna merge it with all of the other pickets. And I only want it to exist on the first frame, so I'm just gonna use a switch. And feed this with a null. And I'm going to keyframe this switch to be 0 at the first frame. And then on the second frame, I want it to be 1. Now let's see, we got the pickets. And then later, we got the other pickets as well. Let's hook this up to our system. And let's go down here. This picket, after the remesh node, we got 1500 points. Let's see what we have in the Vellum solver. We got 3000. So yeah, we got 2 pickets on the first frame. So not only do we have double the picket, so that's not great for the simulation, but it's also gonna make our point deform mess up, like you see. Because the topology of the rest geometry, that is this one, has 1 fewer pickets than the geometry entered in the solver. So to fix this, we can, for example, just go back into the Vellum solver, and I'm just going to keyframe the activation of the Vellum source. And on the first frame, I don't want it to do anything. Only on the second frame, I want it to activate. So on the first frame, it's 0, and then on the second frame, it's activated. Now if you play the simulation again, let's go up here, reset the simulation, play, and you can see that we have 1500 points, which is only 1 picket. And our point deform is working again.